I didn't know.
Donc ouais, celui-là.
D'accord.
Celui-là, il est 3 rouges.
CO2. Anyone know what a desirable amount of CO2 in the room is? No, I mean,
Below 1,000 parts
below
per
1,000. Okay, good. All right.
Already.
Yeah. Okay. Good. Yeah. Yeah, you would think, as a physicist, I'm supposed to know these things.
Okay, so well, it's a pleasure to have Paul FENDLEY from All Souls College, Oxford, who's going to tell us about the use of lattice topological defects.
It's not next to Dana. Having me scheduling this hopefully very informal seminar. So I'm guessing most of you have heard there's kind of a thing going on now. A current fad is non-invertible symmetries. It's a good buzzword. Lots of good work going on. But you know, in all times when there's a lot of papers being written, let's say not all of them perhaps are really groundbreaking results. You get a lot of, well, we're going to take some old result and rewrite it in this new way. And of course, that's very illuminating. But then cynics like me can sort of say, well, what have we learned? Anyway, so what I decided to focus on, try and focus on, is telling you some of the things that I think are really nice, a few of the nice things that are results that definitely tell you something that you didn't know before. And so I'll tell you that. But I will spend probably about half the talk trying to orient you to the way we do these things. And we is a couple of papers I wrote with Dave Asen and Roger Munn a while back, and then last year and year before with Louis Eck, who was my student, but now is postdoc at Caltech. Right. So I think I can't remember what title I gave for the talk, but I put topological defects there. But the non-invertible symmetries that I mentioned before are generated, and I'll be very precise about what I mean by generate these things. But what a topological defect is something you change. If you're in a lattice model, you would change the local Boltzmann weights. If you're in a field theory, you would change the action, whatever. But along, let's say, well, I'm going to stick in this talk with two-dimensional space-time. So think of a 2D classical system or a 1D quantum system. And then you do something funny to the system along these lines. And what the A's, B's, and C's are just labeling the different kinds of defects I have. And again, I'll give you very explicit examples. But the thing is the partition function. So this box is just my picture for the partition function in the presence of these defects. They're topological if I can deform these locally without changing the partition function. So you do have to keep track of how they branch and fuse, and you do have to keep track of how they go around any cycles. If that were the torus, then those A and B defects are wrapping around. Now, it depends on what audience. Probably here, I don't know, I guess. Well, I don't know. There's probably a combination of people who prefer Hamiltonians and people who prefer transfer matrices. But kind of everything I do works for both. But just so if you want a Hamiltonian formulation, you make a time slice there. Something I won't talk about, but very much as part of the story, is you can do this in higher dimensions instead of just lines, surfaces, and the surfaces can be of any dimensionality. So these things are not what people in the old days would call symmetries. So they call them higher symmetries now. And so you notice I put these things in quotes. And the reason is because if you look in a quantum mechanics textbook, it'll say, well, what is, when it's trying to explain to beginners what a symmetry is, and it'll say it's a unitary operator that commutes with the Hamiltonian in a quantum system. But these operators are not unitary. And sometimes they're not even invertible, at least generically in the example. And so that's well, I put it in quotes. Nowadays, nobody bothers with the quotes anymore, but just want to say, and the same with dualities, what the word literally means, right? It's dual, the two things are equivalent. You map from one, then you can map again. You do a duality transformation twice, you're back to where you are, but in these things that doesn't happen. So, yeah. But again, the quotes I think were omitted, at least in most of the following. But and certainly in the literature now, nobody puts quotes on it. But I thought I'd emphasize. So yeah. So even though the setup is going to take me a bit, and again, feel free to try and derail me if I'll try and go through as quickly as I can reasonably go through. But I do want you to understand sort of how it goes, and then I'll kind of run through all these uses. So I probably won't get to all of them. I'll try and at least flash them, and then if people want to see more. So these are various uses. I won't run through what they are now, but when we get there, we'll get there. And so there's 6, like I say, so I'm not going to have time to explain all of them in any depth, but the audience can determine which, if any of them, you want to hear more about. Anyway, so it's just to orient you, the canonical example of what I mean by this non-invertible duality or a defect is the Kramer's 1A duality of that symbol. So it's a very, very old story. But in the original formulation by Kramer's in 1A, 1941, they didn't talk about a defect. It was a mapping of states and partition functions. Many of you here probably know that very well. But then thinking about a defect, and so in the picture, such, and I'll go through this a little more explicitly later, but just to say, so it means you have some defect line, a duality defect. On one side of the line, the system is in, say, the high temperature phase, and on the other side, it's in the low temperature phase. But the point is, again, the partition function will be invariant how you move, so you can make the high temperature region bigger, small, without changing the partition function. So it's a very funny object. And so this was worked out in very different, slightly different versions, but all the same idea by people in the 90s. But it's just by brute force. And there's some other, a few simple examples you can do, but otherwise it's not really possible. But there turns out, so one of the great things that started actually close to 20 years ago, people realized there was a much better way to find these defects than just brute force, take your favorite lattice model with field theory and crush through. And it involves some things I'll tell you about, but the general setting is not in link invariance. And especially in a place like Saclay, where lives and breathes the temporally Lieb algebra, these were forerunners of the general setup I'm going to describe. And so the general structure, the buzzword is fusion categories. But the real amazing thing, and I can say, if you define a model in a certain way, and it turns out, without knowing any of the models defined by all these people listed on there fit in this, and it's many, perhaps even many of the interesting lattice models that people might want to study are of this form, and then you get the topological defects for it's automatic. Once you're there, they have these inbuilt, and that wasn't known when people defined this model. So I'll try, and before I get to the uses, I'll try and explain how. And so I would like to say there is such a thing as a free lunch. Just by defining the models, they automatically exercise properties. And since there's lots of integrability people here, well, many of these models are integrable. This whole story is very not orthogonal to integrability. Many of these models are not integrable. It's not an integrability. It's maybe a cousin of it, but it's not integrable. Okay, so the point of this slide is just very quickly. So the point is there's these whole rules that go, this Jones classic work in the 80s, which then, has had enormous ramifications in mathematics. But in fact, the setting had already been there in physics. This temporally Lieb algebra, it turned out, Jones rediscovered it. So he's trying to compute invariance. You have some knot or link in 3 dimensions, but then you project it on a plane, and there's this well-defined procedure to get something that's topologically invariant. And so what this picture is, and it's not a random one, it's one that's going to use. But what it says is, what this procedure gives, it gives you an isotopy invariance. I call this a fusion diagram. It's just a picture of lines labeled lines like I drew before. So the picture is supposed to be, and only trivalent junctions. And the point is of you can then use this procedure to compute what's called an isotopy invariant. And an isotopy invariant means I just bend these lines. So like a topological defect, I move these lines as long as I don't cut them, as long as I don't change what cycles they're going. And it relates this number you get. So that's what a knot invariant is, and you're doing the same thing for this diagram. It's called a knot invariant because it's called isotopy invariant. It has these labels. So it's the thing beyond a knot invariant is we're labeling each of these. And again, I'll get to the rules of how you do that. But that's the setting, and that's what an isotopy invariant is. Some number associated with each of these closed graphs. And if you know a category, you know getting such a number. So anyway, so I'm just going to do this very schematically. So there's now textbooks written on fusion categories and modular tensor categories and all these interesting mathematical objects. Lots of interesting mathematics behind them. For today, I'll be the cynical physicist and just say these things are out there. We know lots of examples of them. We knew examples of this even before the mathematicians codified it, and we're going to use this to evaluate that diagram. So again, the idea is to take this labeled diagram and then define a category, and then having defined that category, that turns that diagram into a number. So what the category is just it's a list of the labels. Okay, so and again, I'll give explicit examples. So one thing to keep in mind, if you know about angular momentum, you can think the different objects are the different angular momentum, 0, 1/2, 1, and so forth, and so on. The one catch in a category for it to follow the rules that the mathematicians like, the list has to be finite. But the idea is very much the same. You have these labels, and then you have these fusion rules, which again you can think of as tensor indifferent representations of SL2 together. And so what you say, you take 1/2 times 1/2, and it gives you some sum, 0 plus 1 in that case, and then these non-negative integers, and just tell you what's going on there. So if this is unfamiliar to you, just think angular momentum with the caveat that there's a little more going on. And then there's some other numbers in there that specify the category, and let me explain what those are. So with each label, so there's a number which is called the quantum dimension. Actually, even in the math world, it's typically called the quantum dimension. Obviously, it came from physics. And so it's a number. And so the point is, so this is one of the manipulations you can do. If you have a bubble, so you have a line coming in, it splits, some more labels, and then it comes out again. Well, then what happens is you can get rid of the bubble with a caveat that has to be the same as that, and then there's these numbers multiplying. So again, that's the way you take that diagram and muck around with it and then turn it into a number. So that's that. And then the one that really governs kind of everything for planar graphs, like labeled planar graphs like this, is you can take an intersection like that and turn that, and these F, they're called F symbols. Again, they're just numbers that tell you this combination is that. And again, field theory, this is like the S channel and the T channel. And so these are 6J, these are analogs of 6J symbols, if you're doing just ordinary algebra. And so the point is you can prove that with these rules, you can manipulate it. Now, of course, so I cut the slide that said this, well, because you're saying words. Now, obviously, I can't just write down random numbers for the D's and the N's. Oh, the last thing, I should have said this, so the point is at any vertex, for you to draw a vertex, the three things there, if I have an ABC vertex, I guess I never drew an ABC, but the RTA, then N RTA has to be non-vanishing. And for this talk, I'm assuming all sorts of simple things of this category, such that this N is only 0 or 1. There's other things. There's no arrow. And more general, you can put arrows. There's all these extra things you can do. So just for simplicity. But everything I say goes through for all those cases, just to make things prettier. I simplify to those cases. So anyway, so obviously there's this, I can't just write down random numbers, but the whole point of, what physics gives you, or the mathematicians have all these very elegant ways of understanding when you can get those things that you might have heard of called the Pentagon equation. so forth. They give you rules that these have to satisfy. But again, my philosophy today is just I'm just taking this as a given. There's nothing else. Yeah. Oh, okay. It's Pentagon effects and operations. All right. So now I want to start to get to the models that I'm going to study, and these are local statistical mechanical models, and where the degrees of freedom live on the vertices. We'll do this again. This works for any graph you want to do. But today, for simplicity, we'll just have the degrees of freedom living on the vertices, the sides of a square lattice. But the Boltzmann weights, instead of being nearest neighbor, I'm going to allow something a little more general. I'm going to allow then the Boltzmann weights to depend on everything around there. And that's I'm just using a picture for the Boltzmann weight. So what this means is some number associated with what these degrees of freedom. So the H is categorized degrees of freedom. If it were icing, you could say it's plus or minus, or lots of other, whatever your favorite examples. Only simplification I've made so far is that there's going to be a finite number of labels possible for the H. And then there's some number, and then the partition function, you take the product of those numbers over all the squares in the lattice, and then sum over all the left configurations. So please, that's just, I presume everybody knows this in some form, and I hope my form is okay. Please ask if it's confusing. And for icing, for funny reasons, I said it's plus or minus. And well, first I'm going to do something funny for reasons that will become apparent. Instead of writing plus and minus for the icing, I write 0 and 1. That's okay. So that's something, I'm doing something a little funnier than, and people who know about integrability know why I'm doing this. But instead of making the icing degrees of freedom live on every vertex, every side of this lattice, I'd make on every other, which is still the square lattice. So it's still the icing model we know and love. I've just done something seemingly slightly perverse. And then there's some number that, depending on whether these two spins are the same or different. That's my notation. But okay, so I said before, let me reiterate because it's essential to what I'm doing. If you define a lattice model with one of these categories, so God or a mathematician hands me a category, and I pick one, and I'll give you some examples momentarily. And then I'm going to use that, and I know it satisfies those manipulations I do. And then I'm going to use that stuff to define the model. And so to define the model, you pick a particular object, just call it rho, one of those. So spin a half, say, in that list of objects, and then demand that the nearest neighbors on this graph, so just being, have to have non-vanishing and rho h bar for the three nearest neighbors. Sorry, the two nearest neighbors and the rho, this special object. So that's the rule to define the space of states in the classical model. And if you want to think in a quantum model, this would define the Hilbert space, the allowed space.
This rho is uniform for all the lattice.
Yeah, but you don't have to do it. Right. Everything I say will work for non-uniform rho. But I'm good. Stick with you.
So privilege one direction by putting this condition on a row.
No. It's true for any nearest neighbors. So I'm not privileged yet. Any nearest neighbor. Yeah. Right. Any. Yeah. So yeah. So anytime it's a nearest neighbor. So if you wait, yeah, I'll draw a few more pictures. And so I keep saying I'll give you an example. So let me now give you an example. Maybe I should have done that first. So I mentioned, think of SU2. So we label the things in the usual physicist fashion. Always traumatizing to talk to mathematicians because they ask why one starts counting with 1/2, which is a sensible question, but we have historic reasons for doing that. But anyway, we 0, 1/2. But I say to make it a category, we have to truncate it, and the name of this category associated with this is called SU2 level K. People know conformal field theory. It's a thing that arises in that conformal field theory. And so the fusion rules, well, okay, so the 1/2 times 1/2 is 0 plus 1, just like normal. But then when 1 goes with 1/2, well, there is no 3/2, so it can only give 1/2. And I can draw a picture, and so what this picture means is, well, this picture is symbolizing fusion with a half, right? If I go from 0 to 1/2, I get 1/2, so that's why that line's there, and I go 1/2 with 1/2, and I get 0, 1. So that picture is just a shorthand for these rules here. But now I apply this rule to my lattice. I just said nearest neighbors have to, so I'm setting rho to be 1/2, and so the nearest neighbors have to have non-vanishing fusion with 1/2. And so 0 has to be next to 1/2. And then 1/2 can be next to 0 or 1. But so in this particular case, the 1/2 on one sublattice is only 1/2 because of this rule. So that's the reason why I did that funny thing before. It's just the 1/2s that are living on sublattice. And so that's how I'm writing the Ising model. And so it's still the Ising model. So if you do the 0, 1s, those can be whatever you want, and those are still living on a square lattice, just one rotated by 45 degrees. No, it should. So there's nothing going on this sublattice. And this one, so if I remember, good you asked that, because so in my original definition, my interactions were around any square of the original lattice. So in this new funny thing, it just translates to nearest neighbors.
Why are the 1/2s on this half of the lattice and have it shift all the 1/2s by half? By one, that's another reason. For example, the second side is 1/2, but why is not the first side is 1/2?
Yeah. It's two copies of Ising, but it's a sum of the two models, right? Yeah. So usually when we say two models, we would mean the tensor product of this. Yeah. So right. It's in fact, yeah. No, that's good. I will come. That's a crucial thing, and I'll come back to that in a bit. Yeah. Thanks. No, that's true. But yeah. Right. So yeah. So you specify a boundary condition that singles out one of the models. Yeah. Okay. Good, yeah. Good, yeah. I said I wanted to spend a while getting this right. And so again, you have other examples. So this has lots of names. So this is instead that you use this fusion rule. So in a way, it's simpler than Ising, and you just have two states with the rule that only this state cannot be next to itself, and then this state can. That comes up in various guys. There's another one, and if I have a few minutes, I'll say a little bit more. Again, so there's three states, but 0s are always next to 1s, but 1s can be next to themselves, so you don't get this sublattice thing. 1s can be anywhere. So you can think of the 0 and 2. So in this case, you can think of 1 is. I'll give you a more intuitive explanation later on. Right? So there's other examples. But the key thing, and so now I said the point of doing this, not just because I like mathematics. I do like mathematics. The point is, if you define the lattice model, you get in using this fusion category, then you get the topological defect. So let me outline how that goes. So anyway, so now we can draw these pictures, and so these are objects in the category 0, 1/2, 1, and then we specify the row. So I should have it's over there. The reddish lines are labeled by row, but then I can define the Boltzmann weight in the following fashion. So this is just some number, has nothing to do with topology. I can specify it to be whatever I want. But then I draw this picture there. But then by evaluating, but then you define the partition function like this. So this thing is what I wrote down in before. And then to find the partition function, you sum over this beast. I should have put those things on the same slide. You sum over this beast with those numbers, pick to be whatever you want, nothing constraining them. But then you evaluate the graph using these rules. So you turn that graph into a number that's isotopy invariant. And then you get a partition function. And for example, if you do the Ising model, you can rewrite it in terms of loops, but the other way. But that's a non-local thing. But what it turns out, because the beauty of how this works out, you can check if you just want to write it in terms of the Ising degrees of freedom, with the things I called 0 and 1 and 1/2, then there's some formula, it doesn't matter what these are, but there's some formula involving the category data, these F symbols. Yeah.
Where are the edges on the right diagram?
The edges.
Edges. The H1, H2, H2 prime, H2.
Oh, yeah, sorry. They're living in between there, right? So this says what this means, right? But yeah, so let me draw one more picture. So the way, so this lets you define a transfer matrix in the following fashion. I should have put another picture. I was too lazy. But this beautiful blackboard, let's use it. So if I draw this picture. Okay, so this, now think of a line across my thing. So now I pick a direction for this. And remember, so the rule for things to be adjacent to each other was that you use this. So this is a picture. But see, now that picture I can glue on top of this. And now I can do these manipulations to get rid of this. So this sends this to a sum. So if I just do this one, so let's do capital H1. We'll just call, I'm labeling this thing H1. Then you do a bunch of manipulations, and this is where you get those things. So it defines. So yeah. So it's a. It seems strange. I'm going to a lot of trouble to define this thing, but one thing it tells you right now is the partition function you get by this evaluation, by drawing those pictures, these loop models, which people in Saclay like very much, gives you the same answer as this local Boltzmann weights. And if you do this Rising, those F symbols you just muck out and you just get the Ising Boltzmann weights, which is just one number for the same and one number for the. But yeah, this is kind of the I'm trying to think. Yeah, that's almost it for the sort of introductory. Then I'll get to the applications. But this is.
The diagonal there is the projector.
Yeah, yeah. So right. So that's this thing, which is, I guess I call it P. Well, this is the sum. Sorry, H is P. Yeah. Sorry. This is P chi. So this would be. Yeah. Sorry. I just added that last night. So this thing is sum of A, the if you're in the height model. And then you can write it in terms of these loops and things like that. That's my handwriting is terrible. That says in height model. And so
So the Boltzmann matter depends on what you chose from A chi.
yeah, right. And that has nothing to do with topology. And in everything I say, I'm about to say, you can pick A to be whatever you want. The defects. Okay. So that's the definition of these models. And sorry, I wanted schematically because I wanted to get to the applications, but I hope at least the idea was clear. Okay, so I said now the payoff of putting this work in. So it seems, again, it's a lot of effort to introduce this category and write down the Ising model, something probably everyone in this room knows what it is. But now it actually, it's the proudest moment of my career, maybe. We wrote a paper on defects in the Ising model, and I think there was actually something new. So my greatest achievement, I said something new about the Ising model in the year 2016, which I never thought that would be possible to say something new about the Ising model, but I think we did. Anyway, so the way you make defects, and now I'm going to be very schematic, but hopefully clear. So basically what I said, if you remember at the very beginning, I said to make these defects in a lattice model, you change the Boltzmann weights. And the way we do it is basically, so the squares are where I'm labeling just the ordinary Boltzmann weights. That's the definition of the model. But then these things are what I'm adding more Boltzmann weights, so they depend on all four heights around there. And that's how I define my defects. You can do more complicated things, you can do less complicated things, but that is my definition of a defect. And the one that the category is. So then the partition function is the same idea. You just take the product of the Boltzmann weights for each of the squares of the original thing, and then you do the same along this defect line. And of course, we want to find defects now where this partition function doesn't depend on the path of the defects. So in other words, we want to take a given lattice model and then define this thing. And then if you want to think in a Hilbert space or a transfer matrix thing, I can stretch the defect in the spatial direction, so times that way, and then define an operator acting on this Hilbert space. And call that D. So the point is, so now I'll just outline how you prove it, but I'm certainly not going to prove it. But the point is, for every object in the category, you define the lattice model in the way I just outlined. You get a defect, which is, so that's the free lunch. That's what you just get for free. And so it has to basically satisfy. So it commutes with each of these individually, which is nice, and that's why it's more general than it. And why I drew the yellow here. So this is the defect line. That's the Boltzmann weight. It says it's just the same. And this is an equality in the partition function, meaning so anything internal has to be summed over. So that's why I have to sum over this internal spin. But now why I drew this as yellow colored and that it's clear is because the model doesn't have to be the same on both sides. That's like Kramer's winding duality. So it could be, and then that's a symmetry. If it's not the same, it's a duality. But the defect's still topological. In general, could be an interface between two different models. And so if you think, so it sort of commutes with the transfer matrix. And what I mean sort of commute is the following. Okay, so that's that horizontal defect line I just defined. So I can just keep applying this relation, so move it up like that. And then, of course, then I say I do periodic boundary conditions, then I move the whole thing up. But see, now I've changed models. This is now the yellow model, the dual model. And so it's not really commuting with the transfer matrix. It says you commute it through and the transfer matrix changes to the dual model. But like I said, and emphasize again, once you build the lattice model, you have a solution for every object in the category. And moreover, you even know how when you stack them on each other, they obey exactly the same fusion rules as the category gives you. So this microscopic definition, if you wish, now gives you this macroscopic property of what happens when you put defects together. And so to prove this, there's multiple ways, and I won't go into this, just to tell you a language. So as usual, as stuff gets reinvented by different people in different ways, but the field theory version of the proof of this, the one that we gave in our paper, is now called SIN-TFT. It's approach. But anyway, you asked me about it. But anyway, there's multiple ways of proving it. It almost follows automatically from definition, but us being lowbrow physicists, we actually just proved it explicitly by doing these diagrams. But then, okay, so it hands you all sorts of amazing stuff. So not just that these defects exist, it says stuff like, well, if I have a closed defect line, I can get rid of it. And then I just multiply by the quantum dimension of the line. So in the category, one of the rules I flashed at the beginning is a special case of the bubble removal, is if I have just a closed loop, well, when I evaluate it, turn the diagram into a number, you just get this number, this quantum dimension that the category gives you. But now in this lattice model, something the picture-wise is the same. It's more fun. It said I put a defect, a closed defect, and the partition function is independent. If it's a closed defect, doesn't wrap around any cycle, is the same as if I just don't have the defect, you just multiply the thing by number. And since by these defect commutation relations, we can move the defect wherever we want, says that the partition function of this object, and again, so the partition function of this object, and I can make this as big or small as I want, and these two partition functions are the same up to this factor, this number D. Of the category. And again, I mentioned micro to macro. So there's a whole story, and this is where I did something new in the Ising model. So you can now define how the defects themselves branch. So remember the very first picture I showed had defects branching. So the category actually tells you how to define all that. So the whole thing is still, you can even have junctions of that. And as far as even for icing, that was a new result. No one had written that down for icing before we did. At least not that. Okay, so let me just show you. I want to get to the general things, but this is, I don't like being too abstract. Here's the answer for icing. So remember the category I said was, well, 3 objects, 0, 1/2, and 1. In icing world, if you know, heard this, often they're called 0, sigma, and psi, but in the icing world. So I said you have one category for each object. Well, the spin 1 object, that's easy, because its fusion rules, it just goes to itself. So that turns into the spin flip defect. So this is just saying you cross this line and you flip the spin on the other side. So that's a symmetry of the icing model, long known. That topological defect was, of course, known. But the less obvious one is the duality defect. And this is the thing when I drew the thing. And so now this is where the point about the 2 models is relevant, because when you do this duality defect, I make it so I shift the spins from one sublattice to another. And this is the statement that if you know about Kramers-Weinberg, the icing model on one lattice gives you, you do the Kramers-Weinberg duality, it gives you the dual model on another lattice, and with the dual couplings. And this is naturally built into this just simply by saying, well, when I cross this defect line, I switch the sublattice. And if I had done this on a more complicated lattice, it would be even more transparent. How it was going to be. So that's why the 2 copied. So it's really, it's not really a duality. Well, so, it's taking model on one side, on one lattice, is now, it can be separated by the duality defect. Anyhow, I can shrink the regions, which is, okay, so finally, okay, good. So now I'm going to go through, let's see, I have 25 minutes left, so good. I'm sorry, I can at least dawdle on some of the uses, but I want to, before I get to the useful applications, if people have any sort of really overriding questions, because a lot of it I said very schematically, so there's lots more to say, but if anyone has any questions, good time to ask them. Yeah.
Is it usual symmetry, like inverted? Let's say you want to include some U1 symmetry. Is it clear how to include
Yeah,
that?
U1s are weird because what you would, yeah, I mean, you can do this, but I mean, there you exponentiate, you would take a generator and exponentiate it. And these things are weird to exponentiate. And I mean, obviously you can write an exponential if you want, but it doesn't, I think that's just kind of that's just simply the wrong way to do it. So yeah.
So they don't fit nicely.
They don't fit easily into this. And so when people doing these things in higher dimension, yeah, so they don't, you can fit them in, but then that's a more general structure than what I'm talking about. I should mention, so I talked about fusion categories, but you've like Frank Verstraete and Grube, Lawrence Ludens, they showed if you go to module categories, you can, this is a special case then. This is the simplest and by far the most important, but then there's more things you can do. I don't know whether you can fit U1 in that or you have to go to something. Yeah, mathematicians have now spent a lot of time on these, so you can probably find in the mathematical literature what the appropriate structure is, or at least, but they don't fit in naturally. Yeah, so none of it.
I guess you could say, I mean, these are the simple lines are more like the group elements, right?
Yeah.
So now you would have a continuum of simple lines.
Yeah, exactly. Yeah. I mean, more is just, I think of these in terms of algebras. And, this is very algebraic. I mean, this stuff, this is very algebraic, right? Not the way I think of this as algebra because the defect lines satisfy this algebra. They're not invertible, right? So that's,
right. But if it were an invertible symmetry, there would the simple
yeah,
be labeled by the group elements.
Yeah, exactly.
Okay, maybe the group algebra.
Yeah, no, I think we're saying this. I'm just saying, making the point that, yeah, well, because nobody really thought about these kinds of symmetry, this is why, to some extent, Kramers-Weinberg duality was people did sort of obvious generalizations of that, but nobody did anything non-trivial because the setting until people did this fusion category stuff, because it's not a group, so there was no obvious way to think, oh, Kramers-Weinberg duality is just the simplest example of this, that, and the other. But now the fusion categories tell us that's the thing. And then turning those into a group is what that means. I don't know. Maybe.
I think historically that's how this came, because the people were obsessed by the commutative group where the representation and the group are isomorphic. That's how this concept of Hopf algebra came.
Yeah.
And so in fact, the group was important. I mean, even commutative group was the most important.
Yeah, exactly. And then, so, I mean, that's just because, like I said, in the quantum mechanics textbooks, that's what God or Dirac told you. This is what a symmetry is, but now these just aren't that. And yeah. But yeah, and so, I mean, some of these, I think these are simpler. I mean, once you understand how a category works, which isn't that hard. I mean, don't try and read math papers on it, but there's good papers where you can have explained what you need to know for this. Obviously, there's lots of interesting things that you might want to know, but just that this to apply to this. In fact, a big question, even when people classify these categories, there's all these different categories, but we've never been, like there's the ones with the fusion rules of Ising. There's like 8 different categories that have the same fusion rules. But as far as we can tell, they all lead to the exact same lattice model. So clearly, this is using only a subset of the information, even of the simple categories, much less these complicated. So anyway, but then there's a question. Well, this other information in the category, probably there's some useful physics in it, but I don't know. And maybe that will answer this. Anyway, okay, good. Right. So let me tell you about. I could say, so I gave 6 uses. I'm not going to have time for all of them, but I'll go. This first one I'll go through slowly, and then the audience can rush me on through the others, or make me talk. Okay, so this one. So again, I said this quickly. I say it again. Just by building this thing, you know how these defects fuse together, which is just already remarkable. And so let me give an example. So if I take I'm taking Ising model. Instead of writing 1/2, so I did change notation. This is D1/2, D1/2 is D0. D0 is the identity defect, plus D1, which is the spin flip defect. So what it says is I can now define a partition function like this. I put a duality defect here. So on one side, it's the Ising model. The other side is the dual Ising model, dual couplings on the dual lattice. And then here I put another one, and then I go back to the original model. And it says that this partition function, and again, these two things don't annihilate. The fact that these things fuse to this is what makes it non-invertible. Well, so you get 2 terms. You get the identity defect, so the original model with no defects, but then the partition function is a sum over. So this is the non-invertibility. Because the duality, if you wish, the spin flip defect squares to 1. Flip sense twice, you get nothing. So since this upper squares to 1, obviously. So that's what's non-invertible. Some people like symmetries. So we wrote this long paper trying to explain, okay, don't think of duality symmetry. This is what I showed you is the best way to think about blah, blah, blah. And of course, people like to think about things in their own way. And so what Seiberg and Chow pointed out is that you can get a symmetry. So in general, let me emphasize, Cramer's quantity duality is not a symmetry, even if you're at the self-dual point. So the yellow, if you wish, the yellow is the same as the white if you're at the self-dual, but it's on a different lattice. But even if you say, okay, I'm going to work in the Hamiltonian formulation, so it's a line, it's the same lattice. Okay, but even there, it'll change the boundary conditions when you do this. But then what Seiberg and Chow pointed out, actually, which everybody knew, but they pointed it out very clearly, if you go to the critical point, you take the Hamiltonian, you take periodic boundary conditions, and then you do this duality, and then you relabel, so you're going to the dual lattice, but along a line, I can call my sites 0, 1, 2, 3, whatever, and then the dual one, I label half, I'll call half, 3 halves, and all that. Oh, but if it's just a line, of course, I can relabel 1/2 to a 0 or to 1. And that ambiguity says when you do this twice, though, you now mix the duality. So it's a symmetry. So it's the same Hamiltonian. So this is a real symmetry, not an invertible one, not unitary. but then now it mixes duality with translation symmetry. And why I like the way I described is it shows duality has nothing to do with translation symmetry. If you want to make it a symmetry, you have to mix them together. Sure.
In the old days, people were using temporary and just the translation of one on the temporary.
Yeah, well, it's the same, right. No, it was the same in the fermions. No, in fact, I'm now in my mellow old age, but in 2016, I was a young man 9 years ago. People would helpfully say from the audience, in the usual physicist fashion, I do it too, oh, I thought duality was just this half translation. And then I would get mad and say, well, but that misses the non-invertibility, because it says you do duality twice and it's a translation. And it's not, it's 1 plus spin flip times a translation in the Seiberg cell. So, but that's important because it annihilates half the states. The projector 1 plus spin flip annihilates half the states. So it says duality isn't defined on half the states. So that is a somewhat, conceptually. And it's the same with temporally relieved too. If you're doing spins. So actually, the other category, the next simplest category where the fusion rule is just 1/2 times 1/2 equals 0 plus 1. So again, D0 it's called the Fibonacci category, and it's got a bunch of names, golden chain, things like this. So again, this one actually is invertible, but it's actually a symmetry. It takes the model to the model. There's not the above categories. So, but now for any category, you know that you have all these things. And I believe, it's certainly not proved, that there will be a lattice model built from a category for any rational conformal field. Certainly not proved. You can come up with an RCFT that I wouldn't have no idea what the lattice model is. But there's lots of lattice models that you can make from categories. So there's lots of RCFTs. But in fact, lots of examples I know, there's typically more than one lattice model of the type I've described. It describes all the CFTs I know in a simpler CFT. So that's not proof, obviously.
What's missing?
Sorry?
What's missing? It seems that you have showed us how to build a lattice model.
No, I can build all these lattice models, but then you have to then go down the list of every coset conformal field theory you find, and I have to then find the dictionary from I have to find the category. And so the RCFTs have categories, but the category for a given RCFT is not necessarily the same as the category for a given lattice model. In fact, that's why there's more than one, because I believe, again, not proof, is that the category of the lattice model that I use to build the lattice model will be a subcategory of the category of the RCFT.
You always use the whole category to build some lattice.
I agree. This is why I think it's true, but it's not. Because like I say, the two aren't necessarily the same. So there could be the weirdest conformal field theory that even if you build a lattice model from that category, anyway, I think it's true. And you're not supposed to parse this picture, but the point is people are sometimes too spoiled by the icing case. So this is just a 3-state model. People have heard of the 3-state Potts model, but Eric knows because we wrote a paper on it. There's another self-dual coupling a nearest neighbor self-dual coupling in a 3-state model. So you can add to them, and then they're invariant under the Z3 generalization of Kramer's finite duality, which from the category language is called the Tambari-Yamagami category. But it's a very natural generalization of Kramer's finite. Long known, long before Tambari-Yamagami people knew about this. But anyway, the point is you add these two things and you get this phase diagram. So the point is you just write down one of these lattice models in general. You don't know what CFT, I guess that's partially, you don't know what CFT you're going to get. And in fact, you get multiple ones. You get things that aren't even CFTs sometimes. You get gap phases. You get critical ones that aren't CFTs. And you get a bunch of CFTs. So it's a whole zoo. We're spoiled with the models we spend most of our time on. So I just flashed that there again. You're not supposed to be able to read that. Just show there's lots of different things going on. And at least 3 different CFTs. And at least 4 different CFTs. All right, so how much? About 10 minutes. So good. So another thing you can do is use this symmetry. I'll remove the quotes. use the symmetry to drive degeneracies, non-obvious degeneracies. So there's a result from perturbed conformal field theory, very funny theory. It's a certain perturbation attractor lysing model that you can think of it as two degenerate ground states, but they're not symmetry related, not just like spin up and spin down. So, but they're exactly degenerate, and you might think that has something to do with it. Well, maybe it does, and people understood it. You could understand it then eventually first seen using numerics and then quantum group algebra. But something I'll go through quickly and slow me down. If you want, you can actually take a lattice model in this universality class. And the lattice model isn't integral. The field theory is, but the lattice model isn't. And you apply one of these symmetries, and then this degeneracy just follows. So I'll just quickly say what the lattice model is. This Fibonacci one, again, has lots of names these days. This model goes back to Baxter and what he called hard squares. And so it's, again, this rule spin one, but we truncate it so there's no spin 2 there. And it has that picture. And sometimes I hang out with condensed matter people. So this would be this model where you have a Hilbert space like this, which we call the Rydberg blockade, because I said this quickly before, but read it again. So you can think of this as an empty site because it can be next to itself. And then you think of the zero states as particles, with the rule the two particles can't be next to each other, and they can really, atomic experiment, cold atom experiments, they can really tune this by using beautiful properties of Rydberg. It's unbelievable that they can do this easily. They call it the Rydberg blockade. But so there's a certain Hamiltonian that does commute with the symmetry. And I flash it there because I'm in Saclay. I'll flash it quickly, but probably a good percentage of this room knows exactly what that Hamiltonian is. But anyway, acting on these states, and the reason why this is the time to leave it. Vincent's famous paper from long ago, he called this the A4 case. So actually, I didn't even put that up there. This should have been a fifth name.
I should have taken the quotient, then I would have been called the golden chain.
Yeah, exactly, right. No, the golden chain, yeah, was, it's a good name. You have to admit, it's a good name. It really is. But they discovered, so I should say, I gave them credit because they discovered the symmetry. So even though the model was known, they didn't know it was known, but it was known by many, including you. But they, as far as I know, nobody knew about the symmetry. So that's.
I think Yvan wrote a lot of papers about.
Yeah. Okay. Yeah, it would be interesting. Well, I should ask Yvonne if that really was there. If it was, I didn't understand it, but maybe it was. Anyway, and so the fact that I mentioned here, the symmetry each of these pieces of the Hamiltonian commutes with this individually. The point is then you can go to an extreme limit. You just throw out half the terms, you solve it, but then you see this non-invertible symmetry. So I didn't write out what it is, but it's easy to see. The non-invertible symmetry just maps between two different ground states. There's two different ground states in this extreme limit, and the non-invertible symmetry maps between them. But now you know. So this is a trivial limit, but now we turn it on, but the non-invertible symmetry persists. So the degeneracy can't be split until you go through phase transition. So you know as long as you're in this phase, you have these two funny ground states that are not obvious symmetry related, but now we know what the symmetry is that relates. Oh, it's this. And so the exact degeneracy. And actually, and the same argument works even for the low-line excited states. You get which was again observed from the integrability, but again with the same argument gives you. So again, are even more peculiar degeneracy? I'll explain that more in questions. But okay, well, still 7 minutes. So okay, so this one I'll go through quickly. But again, so if we take the next model of the one I did, so. Again, spin 1 times spin 1 gives me 0 plus 1 plus 2, but then I truncate it there. So now I can, instead of thinking it as this Rydberg blockade chain, I can think of it as a Rydberg blockade ladder where the 0 and 2 are living on the two different legs of the ladder. And then 1 is the empty, and that can be anywhere. And the rule says that basically you have at most 1 particle per square. So more than just nearest neighbors. So I guess the radius here is now square root of 2, so you can't have ones because 0 can't be next to 2. So it's a special case of the Rydberg blockade ladder. And then you find it's a family of a whole of models, a whole bunch of models. There's these non-invertible mappings when you go through the category. And you have to do some other stuff. So this is where if you want to put it all in the correct category language, you have to put it in modules. But you can just work, you get an orbital defect and other stuff. So again, you get this relation like I wrote down with the transfer matrix. So this is the XXE chain. So it turns out there's another model. You can think of it as 2 coupled Ising models. And you do this non-invertible mapping between the two. And what again, so it doesn't commute with the Hamiltonian. It says when you commute this mapping through Hamiltonian. But one thing, because it's non-invertible, this K, this kappa, has lots of 0 eigenvalues. So it doesn't work on all the states. In fact, half the states are 0. It maps to 0. So there's a more complicated story. But anyway, you can map between them. And then what you can do now is the XXE phase diagram is known since t equals minus infinity, I think not for me, but a few of us maybe old enough to when that was figured out. We've definitively figured out. I think it predates even me, the people. But anyway, in the end, for those of you who know, that's the CFT, but we'll talk about that in the scapless region here. But then by this mapping, we know the phase diagram for this other one, as long as the ground state doesn't get squashed by the mapping, is this. So this very complicated integrable Rydberg ladder, because XXE is integrable, you do this mapping, the other one turns out to be integrable, highly non-obvious, but it's true. Then you know its phase diagram. Well, not quite instantly. You have to do a little work and reinterpret. And what you get here, what's in the gap phase, so in XXE, it's just 2 ground states, the 2 states of an antiferromagnet. When you do this map, it's 3 ground states and not symmetry related again. That's kind of cool. So you can see the same phenomena that I described just a little while ago. And again, by the same argument, you know these 3 phases have to coexist in this whole region because of this because of a non-invertible symmetry. Right, a few more minutes, and right, oh yeah, 2 more. Good. And the one I like the most, I remember Bear. First time I told him this guy, very annoyed with me for some reason. Happily he's not here today, so well, not happily, I wish he were here, but he's not here, so I can say this. But anyway, yeah, so all these G factor ratios, for those of us who were around in the 90s, we spent a lot of time, but even I think probably most younger people have heard of this. So the G factor is in CFT, it's like a central charge, but for boundary conditions. And there's a G theorem that says it has to go down. And in CFT, they're easy to compute, but from a lattice model, we don't know, but from this argument, we can instantly get ratios of the G factors by this following argument. So it says, so we start with some model, okay, and we have some boundary condition. I'm just calling that B for the boundary condition around the edge of the disk. Well, okay, I can nucleate this defect. And you remember, I said the partition function just changes by that 1 over d. So the other one will nucleate the defect and divide by the 1 over d. But now I can move this defect to the edge. It's topological. And now I glue the defect to the edge. Think of it as an operator acting on this edge. It changes the boundary condition, but I've now got an exact equality of partition functions with boundary condition B and then boundary condition dB. So if you do this in Ising and then act with the duality boundary condition, fixed goes to free, turns out, when you just work out what's going on. And so then we now know exactly. So this is the definition of the G factor. And so, I mean, literally no work. I mean, people observed they were these quantum dimensions before, but this gives a lattice proof of this. With this definition of the partition functions, you can quibble. I think that was Zuber's objection. Wow, I picked a particular definition of the partition function, which is absolutely true. Yeah.
I thought these different boundary conditions with non-identity G ratio would be related by an RG flow. Right?
Yeah, they can do that. So what that would be is you would change. So right, you change, but you would go out of the CFT. Right, you would say you would say, I'll add a perturbation. And then I go, absolutely true. And that's what the G theorem is.
Yes.
But this just says,
It sounds a bit funny that you can get boundary conditions by doing topological things instead
but
of
yeah, changing.
Okay.
I mean, yeah. No, I say I can move between, but the key thing is, this doesn't prove that I had a conformal boundary condition to begin with. Like, this just relates to, so if it were a conformal boundary condition, then it's, well, this is a true statement no matter what the boundary condition. However, it only means G if there's the traditional thing. But no, right, it just says, it just relates this model to that model and says, within this definition of my boundary conditions. Yes. And it's just the quantum dimensions. And of course, it agrees all known examples if this works. And so for example, in Ising, you get the square.
The G theorem said something about quantum dimensions can be bigger than one, smaller than one, but boundary conditions.
Well, no, but quantum dimensions are always greater than or equal. So the G theorem is the fact that quantum dimensions are always greater than or equal to 1.
Oh.
So if you do a dimension 1 defect, that says that G's are the same.
Yes. So, but you know that B flows to d phi B.
Yeah, right, because that's where.
Yeah.
But for example, if I did the spin flip defect, it would just spin. Well, for free boundary conditions, it wouldn't do anything, and for fixed boundary conditions, it would just flip all down to all up, and those obviously have the same key. Right, but then for anything greater than 1, it says. Right. So you always are going to increase the boundary. When you do this thing, you're always going to increase the boundary.
I see.
Yeah. And I wanted to say one more thing that I love because I think this in a way is maybe my favorite result in these papers. You can so I won't go through the details, but you can get. So by doing, show this picture. So again, now let's think on a torus and we stretch defects. But now we do a Dane twist. So what a Dane twist is, you basically just cut your torus, or it doesn't have to be a torus cylinder, and then you twist by 2 pi and glue it back together again. But we know in CFT if the lattice model is a CFT, so we'll now assume that we have some lattice model that we know is a CFT. And for the Ising case, that's been proved by Smirnov, but in general, we know lots of examples of lattice models that, even if not proved, we're confident they go to CFTs. And so now I do my defects in this. But the point is, in a CFT, the eigenvalue of the Dane twist is related to the dimension of the operator that creates the defect that's running along the cylinder. So you do this Dane twist, which usually is called T, and so twist that around. But then I can work out what the eigenvalues are just using all this category. So it's rather simple to do. Just by using the algebra and the F moves, you can work out what the eigenvalues. And what you find, it's a phase, which is good, what you expect from a CFT. But then the phase in the CFT is related to the dimension of the operator. So this, as far as I know, is the world's simplest way of seeing why there's some operator of the of dimension 1/16, the chiral operator of dimension 1/16 in the Ising. I mean, you don't need to know one word about CFT except, well, find this fact that I'm identifying this dimension in the CFT with this thing, but I don't need to know anything about representations of the Virasor algebra. And for this Fibonacci golden chain type example. So I really like this, and Dave came up with a more general conjecture relating lattice partition functions to the continuum ones, which still has never been published to show it because I've been simple. Okay, good. So now I'm out of time. Oh, I'm over. Sorry. So anyway, if you add braiding, there's some other cool things you can do, but I won't tell you about that, and I will just put my conclusions up and.
So this 1/5 for Fibonacci, if you could go back to that.
Yeah.
Is the statement, so maybe there's an assumption of unitarity here or something. So say the Liang model also has a Fibonacci symmetry. And as far as I know, there's no 1/5, there's a -2/5, maybe something like that. So there are plenty of CFTs with Fibonacci symmetries. Like
No, you have to build it for, it would have to be one built. So again, so this is from a lattice, this is a statement about a lattice model. So what you should view it as is a constraint. You should view it on as a constraint on possible dimensions of if this lattice model turns into a CFT. That CFT must have an operator like this. Now there are subtleties with twisted boundary conditions, and all that. So I wouldn't. So this isn't. Not only is it obviously it's not rigorous, but it's probably not even rigorizable. There's too many catches. But yeah, so that says in this given lattice model, with the Boltzmann weights I chose,
Right.
I don't get Li Yang. So there presumably is another model that I could find, and that actually would be a good check. I agree, it's probably not that different from this one. It may even involve the same algebra, but this involves also assuming that the Boltzmann weights are uniform and maybe in Fibonacci something different. So yeah, so no, it would be a good check, but we never did that. Yeah, we never looked at any non-unitary cases, but because people don't like them for obvious reasons. But I will say the famous words. I don't see any problem with extending these. But yeah, so it's a bit of things. Yeah, so yeah, I forget what the dimension of the operator is. It's minus something. Which is already.
Okay, no. That's like using it as one eight, right? Using the diagonal using has an operator of 1/8.
Yeah.
It's 2 times 1/16.
Yeah. And by the way, this is also up a half integer. And there was a case where I think
Yeah, you have to minus.
Yeah, and there's half because it's some phase and there's a sign ambiguity, so that's why this is all sure stuff. Yeah.
From the data of the category, you can construct a height model which then flows to some RCFT. Is there any?
Well, that was the point of my showing that picture. You get lots of RCFTs, and we don't always know which one, but it seems generically somewhere when you tune the couplings appropriately from the category, you will find RCFT. Probably more than one, but you have to tune the couplings.
Is there any indication that this framework could be applied to find lattice models which flow to some irrational CFT and then construct?
Yeah, I don't think so. Because everything. Well, I mean, sorry. I should say we have no idea. Like, that was the purpose of that complicated picture. Was just anything could happen. So there's absolutely no reason why it couldn't happen. I think, well, Jesper could maybe comment more. I mean, so yeah, so in fact, these models Jesper and co found now 20-something years ago, nearly 30 years. When did you find those? So those are built from coupled Potts models. So obviously you can write those all down in a category, and they have the duality symmetries, which of course they know. So yeah, you could you could run. So one possibility, of course, is that the model that Jesper and co found is not a CFT. It's critical, but it's not a CFT. Jesper can comment, or maybe not. You want to deny your youth. But yeah, no. So in principle, there's no reason why not. And we certainly get we get. You can in these we clearly get critical models that are not CFTs. You get these incommensurate phases, so they're critical, but and very clearly not CFTs. But I don't know about irrational CFTs. I don't know of any examples where I know you get those. But this would be a constraint that if it's a CFT, this should be there. I mean, unless this argument that the eigenvalues of the Dane twist breaks down. So I'm using that I'm definitely using the CFT argument that the eigenvalues of Dane twists are related maybe for irrational CFTs. I don't know why it wouldn't be. But yeah.
Well, I guess we should mention that. I don't know if like Antonio and Junshin here are looking into these lattice models and trying to see if they.
Oh yeah. No, I know this stuff. Yeah. So no, it's a hard question. I mean,
Well, it might. I don't know. There's some numerical indications that these things in some cases flow to CFTs that are not.
Not known to be.
No,
Yeah.
don't correspond to any.
Yeah, no, I understand. Yeah, no, that's why I brought the for stuff long ago. No, I know people have done some nice things recently on this. Yeah, I don't see why. I mean, everything I said in these lattice models is, I mean, it's true. The thing that where something may go wrong is my interpretation of this lattice model then saying something about a field theory limit. Because of course we don't even know that this a priori this lattice model has a limit, but it is absolutely a rigorous fact about the lattice model. And then the murky part is the following part. And yeah, I guess, yeah, from my point of view, when with that crazy diagram, yeah, so this, it depends on the student. Some students really grew to hate me because I would make them do things like that. And then other students, other students, Ed in particular, clearly found his calling because he didn't even need me at some point. This is almost all his work. Yeah, but the point of why I showed this was it is so not cut and dried. And I remember with various friends and saying, no, just because you write down a lattice model, and just because even if a lattice model is really nice to define, you understand exactly some algebra, CFT, and again, people who do this, know this, you just can get all these things. Like, Eric, let me, since you prompted me, I'll tell you something bizarre. Okay, so this point is exactly C equals 3 halves. That's an integral model. So in this chain, I haven't told you precisely what it is, but there's two self-dual couplings. And in fact, this is just the other self-dual. Eric and I studied this one. But this other sign equals. And so it turns out the particular point that this model is 4/5 plus 7/10. It's a product of the tricrystal and the three-state pots control filters. But now you change this coupling. You add some three-state pots into it. It stays critical, absolutely clearly numerically. Central charge, state, well, the entanglement entropy central charge stays 3 halves, absolutely clearly. And if you look at the levels, what it looks like is happening is the Fermi velocity of this C equals 4/5 theory is different from the C equals 7/10. And now we're stuck. It's not integral. We don't. What?
Somehow.
As far as we can tell, numerically, no. But that's just well. This is at the top point. That's an exact result. That's integrable. But once we go, so I'm just giving this as an example of once you go out of integrability, and even in rather simple, this is a nearest neighbor model with self-duality, and has this bizarre thing that at least I've never seen any sort of not true. Yeah, I've seen take Fermi models and do whatever you want with Fermi velocities, but in a just a spin model, nearest neighbor spin model, three-state spin model, a whole heap of symmetry, this duality. That's right. Anyway, so the answer is just that it's a zoo, and that's why CFT is useful because it lets you at least things.
Can I ask you a question? In the slide of S&P transformation, have you been the first one to write them out just with a single left move, or are they known since forever? Someone else wrote down them.
That's a good question. I think So people did these things in CFT for sure, like the Swiss group, Froelich, Fuchs, Runkel, Schweiger. Did things like that in CFT. Whether they wrote out that exact thing, I don't remember, but they could have if they had wanted to. So from the picture point of view, if they had done it, they would have wrote exactly the same pictures. But what we did that I'm pretty sure nobody had done before was make sense of this in the lattice model. So that picture in my case is just a schematic picture. Everything in there, including the Boltzmann weights when the things join is F. And the fact that you can use the F moves for the defects themselves that are the same F symbols that you use to build the models. That's definitely new. But whether they actually, I don't remember whether they actually did this with their defects, but certainly the defects in CFT. And of course ours again has nothing to do with CFT. It's just in the CFT case you might have this. Was that what you were asking?
Yes, it was really,
Good. YouTube, I forgot.
Ça, je pense qu'il doit arrêter. Oui, attends.
Thank you.
Yeah,
Stop screening.
Very nice.